Okay, so now in this video, what we want to do is we want to talk about paper chromatography. Okay, paper chromatography, and I want to talk to you about TLC, thin layer chromatography. Now, in paper chromatography, in this one, paper, what is paper? Paper is actually made up of cellulose. Cellulose contains all of these OH groups because it's glucose, yes or no? Because glucose. So this basically makes paper to be very polar. That is why when you put, if you accidentally drop water onto paper, the entire paper becomes wet and the water almost soaks into the paper. So it takes a while for you to dry it up. But unlike plastic, when water falls onto the surface of plastic, you can just wipe it off. That's it, it's gone, right? So in paper chromatography is a very primitive way of doing chromatography, okay? But it's a basic idea. So in this method, what we do is, okay, so I'm going to draw this out for you. So let's say in this method, what we do is we take a piece of paper, okay? We take a piece of paper and the paper shouldn't be too long. So usually it can be about 15 centimeters long, can be about 20 centimeters long and so on. So what we do is, okay, let me erase this off. Okay, so it's about 15 centimeters long. So what we do is we draw a line at the bottom here. Okay, we draw a line at the bottom here. This line is called the origin. Okay, it's called the origin. And this line is usually drawn roughly about 1 cm from the bottom, or 1 or 1.5 cm from the bottom. Then at the same time, what we do is we draw another line at the top here of the paper. This line is also drawn about 1 cm from the top. Okay, it's also drawn 1 cm from the top. So this line is called the origin, and these two lines that we drew here must only be drawn with a pencil. Okay, you cannot use a pen because pen is made up, has ink, and ink is ink is a mixture of pigments. All right, mixture of pigments. Now pigments, they will separate. So what will happen is if you ever have ink on a piece of paper, the ink smudges all over the place. All right, so let's come back to this again. Okay, let's erase this. Okay, so what we're going to do is, let's say we have a sample. All right, let's say we have a sample. All right, so we have a sample. We want to know whether our sample contains the following components. We want to know whether our sample has something called A, something called B, something called C, and something called D. We want to know what is in our sample. So what we're going to do is we're going to come back here, and what we're going to do is we're going to take our sample and we're going to put a spot of that sample here. Okay, oops, that shouldn't have happened. Okay, we're going to put a spot of our sample over here. Then what we're going to do is, so this is our sample, yes, okay, our sample. Then what we're going to do is we're going to take a pure sample. We're going to take a pure sample of A, okay, and then we're going to spot it over here. This is pure sample of A. We're going to take a pure sample of B. We're going to take a pure sample of C, and we're going to take a pure sample of D. Okay, so we have A, and then we have B, we have C, and we have D. So we take a pure sample of this. All right. Okay, so then what we do is we take a beaker or a tank. It's called a chromatographic tank. But let's say for things to be simple, we take a beaker. But the beaker should be bigger than our paper. Then what we do is we put a solvent here. Okay, we put a solvent here. So this is our solvent. Okay, now solvent can be anything. It can be water, it can be a mixture of alcohols, it could be a mixture of water and alcohols. Okay, so we take our solvent. Then what we do is we take our paper. All right, we take our paper. Okay, let's take this whole thing out here. and then what we're going to do is we're going to put it into the beaker. Okay, not very nice, but we're going to put it into the beaker. So when we do this, right, when we do this, what we want to do is we want to make sure one thing, all right? We want to make sure one thing, and that is that our samples, the samples that we have placed here, right, all of these samples here, they must be above the solvent. They cannot be the same level as the solvent or below the solvent. They must be above the solvent. So what will happen is if you leave it, the solvent will start rising. Okay, the solvent will start rising, and it will start rising, and it will start rising. And the moment the solvent reaches here, the moment it reaches this line at the top here, we remove the paper from the beaker. Okay, so that's what we do. So then, because we allow the solvent to reach till the top here, so this is called the solvent. This is called the solvent front. Okay, solvent front. So which means that what we do is we observe the movement of the solvent. As the solvent reaches that particular height, we remove the paper. Sometimes what they do is they don't draw the line. The experimenter will look at this and will decide at which point he wants to remove the paper or she wants to remove the paper. When they remove the paper, that's when they use a pencil and draw a line to show that that's the distance which was traveled by the solvent. So once this experiment is finished, what will happen is you will notice that these spots here will disappear. Oops, all these spots will disappear. Okay, so I'm just going to do this again. So these spots will disappear. They will no longer be there anymore. All right, they have gone. They have disappeared. So what you may notice now is there's a spot that appears maybe somewhere here. There'll be a little spot over here. There could be a spot that appears somewhere here. There could be a spot that appears, a spot that appears somewhere here. All right, and then you might notice a spot that appears maybe somewhere here. All right, done. Because these are pure substances, right? A, B, and C are pure substances. You will only see one spot. If you see more than one spot, that means it's not pure. Meanwhile, when we're dealing with our sample just now, you might notice that, hey, there's a spot over here, there is a spot over here, and there is a spot over here. Okay, so you see 3 spots, and these 3 spots correspond with, if you notice here, corresponds with this, right? So our conclusion would be our sample contains what? It contains A, okay? It contains A, it contains B, and it contains D. That's our conclusion, all right? That's our conclusion. So our sample contains these 3 samples, these 3 components, all right? That's how we do paper chromatography. Paper chromatography and thin layer chromatography is exactly the same. It's exactly the same. The only difference is in thin layer chromatography, what we do is in thin layer chromatography, so okay, we'll come back to this. Okay, in thin layer chromatography, what we do is, okay, so we, instead of using paper, we have a glass or a plastic or aluminium backing, and then what we do is we coat it with silica. All right, we coat it with silica powder. Silica powder, just like paper, contains all of these groups here. This is silica. It contains all of these groups. So what we do is we take silica. Okay, we take silica, all right, and then we add it to water usually, or solvent, all right, and then we get a mush. Okay, we get a mush, like we get a paste. We get a paste. Then we take a piece of paper. We take a piece of glass. Right, we take a piece of glass or a piece of aluminium. All right, usually about 15 to 20 cm in length. It could be slightly longer, slightly shorter. Then what we do is we take this paste and we put it onto the surface. We coat it, and then what happens is we coat it, And then what happens is we use a device that will flatten the entire surface, so that you see a very nice thin layer, a very nice thin layer. And then we put this into the oven, and then we bake it. All right, we bake it. So then what happens is you will end up getting a silica plate. That means it's like, imagine you have a toothpaste, and then you nicely put the toothpaste onto a layer of glass. You see a nice thin layer. Okay, a nice thin layer. So that will be TLC, thin layer chromatography. It's exactly the same as paper. Okay, so if you look at these pictures here, all right, so this is how the separation takes place. All right, so basically what we say here is what we can look, when you look at this image here, I want you to notice that if you have these components A and B and C and D, you have these 4 components, right? You notice that D travels the distance of D from the origin is the closest. Meanwhile, B is furthest away from the origin, closer to the solvent front. So what we say is we say D has higher affinity to the stationary phase. Okay, and we say what do we say? We say B has higher affinity to the mobile phase. Okay, that's what we say. So in this case, so the component that travels furthest away from the origin is the one that has the highest affinity to the mobile phase. It follows the mobile phase along. And the one with the lowest affinity to the mobile phase will have the highest affinity to the stationary phase. It's closer to the origin. All right. So sometimes when we get separation like this, right? When we get separations like this, what we can do is, okay, like say in this example here, right? You see the solvent is below the dot here. And then what happens is it separates into 2 components here. So what we can do is we can do a calculation which is called the RF. We can do an RF calculation. RF is it basically means, I'm not sure whether it's here, it's called the retardation factor. Oh, here it is. It's called the retardation factor. So, so like for example, how do we calculate the RF value is, first of all, we look for the distance between the origin and the solvent front, So in this example here, the distance is 8.5 cm. Please remember, it's the origin to the solvent front, okay, not the edge of the paper, not from here. Then for each component, we measure the distance. So normally when we measure the distance, right, usually if you measure from the top here, then for this component also you must measure from the top. If you measure from the middle, this also must be from the middle. So it must be the same. So in this case, they measured the distance here, 2.1 cm, and then they calculated the RF to be 0.25. Let's say this distance is 5.5 cm. Okay, so if that distance was 5.5 cm, 5.5 divided with 8.5, I get, for the yellow, I get the RF to be 0.65. Okay, so now I have 2 RF values. One RF value is 0.25, the other RF value is 0.65. So let's say if you're given few RF values, right? You're given a few RF values. Let's say 0.25, 0.65, 0.85, let's say, and let's say you're given something like 0.10. Okay. So when you are given RF values, by looking at the RF value, you can identify which component is strongly attracted to the mobile phase and which component is strongly attracted to the stationary phase. So in this image here, in this picture here, you notice this is the smallest RF value. So the one with the smallest RF value is the one which is most attracted to the stationary phase. And the one with the largest RF value is the one that is most attracted to the mobile phase. That means it's furthest away from the origin. That's what it basically entails. And one important thing is, you see here, We can use the RF values, okay, if, for example, we repeat the experiment, okay, we repeat the experiment using the same solvent system, same paper, same temperature, everything is exactly the same, right? Then we can use the RF values to determine. For example, let's say this same experiment, right? I repeated the same thing. But unfortunately, when I repeated this, okay, so let's say when I repeated this, what happened is, let's say this is the origin. This distance, okay, is no longer, like in this question, 8.5. Let's say this distance was 11 cm. Okay, now the distance is 11 cm. So how far will, let's say, the blue component move? How far will the blue component move? Now from this question, I know the blue component has an RF of 0.25, right? So quite simply what I do is 0.25 is 11 divided with the distance traveled by the blue component. So the blue component will be 11 times 0.25. So 11 times 0.25, 11 times 0.25, I get 2.75. 2.75. So let's say if I had introduced the sample over here, I introduced the sample over here, right? Later on, I can predict that 2.75 cm from here, 2.75 cm from here is where I'm going to find the first component, which is the blue component just now. And then if I want to know how far the other component has gone, I just do the same calculation. I can predict where the other component will end up being. It'll probably be somewhere there. Okay, so that is how I can use the RF values. If I repeat my experiments under the same conditions, I can use the RF values to identify where my samples are. And based on the RF values, I also know which of my samples are there. Like for example, every time I do the same experiment, every time I do the same experiment that you're seeing here, the RF value for the blue component will always be 0.25, and the RF value for the yellow component will always be 0.65. Always. Same paper, same temperature. Right, same solvent system. Okay, so we'll stop here for a minute and then we'll continue.